Can someone confirm we've shared the screen successfully and we're good to go?
I see it. I think we're good.
Thank you very much. Thank you. So a lot to cover. I'm going to start very light. I'm going to start literally with what causal AI is, with pictures and definitions. We can get into the maths, but given the time, I just want to make sure that we spend a good chunk of time on where we're seeing causal AI helping asset managers, and then leave plenty of time for questions. So I'll start with an introduction to what is causal AI. I'll then talk a little bit about model risk and why model risk is an issue and how causal AI helps us there. And then the big thing is around causal graphs and around causal models, and then a few examples at the end on asset management. So for those of you that don't know causaLens, this is the marketing slide that my marketing colleagues make me show. We're doing lots of things for lots of different people in lots of different industries, of which finance is just one part of it. But let's talk about what is causal AI and the causal revolution. So a number of...
Brian, these Omega guys are complaining about the trades not showing up.
Oh,
can we check every day, right?
I'm going to call them now. They just reposted the report and all the trades from yesterday show up. All our positions.
Hi, Chris. You're not on mute.
Dan Amirali. You could call Dan. I mean, Ed's like the CFO guy. He's like
I think can we
Chris, we can hear you.
The boss man over there, but Dan is like the guy who does all the work.
Yeah.
Can we evict people? Maybe we can mute him. Maybe we can. Oh, he's on mute now. Perfect. So a number of people who are far smarter than I think that causality and causal AI is going to be the area to watch for the next breakthrough in artificial intelligence. People like Judea Pearl, Gary Marcus, Yoshua Bengio, they've been talking about causal AI for quite a while. Then it's now being recognized in the public space and the media as well. Last November, the Nobel Prize Committee awarded the Swedish Central Bank Prize to 3 professors, 2 of whom were awarded Professors Angrist and Imbins for their breakthrough or methodological contribution to the analysis of causal relationships. So the Nobel Prize went for this area. But why? Well, the attraction of causal AI is threefold mainly. Dynamic, it's explainable, and it's fair. Now, of those 3, the first 2 are very relevant indeed to investing and asset management. Obviously, financial markets are dynamic. What drives our markets changes over time. And unfortunately for us, the traditional statistical methods were designed for more stable, stationary systems that don't have concept drift. In terms of explainable, well, one of the very large impediments to AI implementation, or for that matter, traditional old-fashioned quant work, was the challenge of explainability. So when someone says something like, why does my portfolio hold this one specific asset? When I used to reply, it's because the off-diagonal covariance elements isn't a great response. Yes, it's an explanation. And yes, it's an accurate explanation, but it's not a very useful explanation to the person asking the question. Or when I was at a momentum-based hedge fund back in London many years ago, and someone asked me, why are we long natural gas contracts? And I replied, well, because the price has gone up and we're a momentum hedge fund. It's an explanation, but it didn't really satisfy the person who was asking me the question. That they want to know the macro reasons behind it. They didn't really want to know the technical reasons. So the explainability is one of the impediments that causal AI helps with. And the last one, fairness. I'm not going to say too much about that today. That's more about modeling individual people rather than assets. And it's about detecting and avoiding bias for lending and hiring and so on. So I won't say too much about that one today, but it is important. So those 3 reasons are why so many people are getting so excited about causality for AGI or artificial general intelligence. But I'm more interested in deploying it for asset management today. We've got a bunch of clients. You can see some names there. These are the ones we can publicize. Some of those are in finance, some others. We've got a lot of other clients that we're a bit more that we don't publicize yet. So general artificial intelligence is one thing, but practical tools to help asset manager and institutional investors are another. Here's a few of the uses that we're already seeing in asset management already. And this is what's going to come later: portfolio construction, human-guided research, evaluating alternative data sets, discovering orthogonal factors, and so on. And these are the demos and the examples that I'll show towards the end. So what do we mean by causal AI? What is it?
Ik probeer er nog even in te loggen van mijn computer.
Well, if we collect data on how often, a simple example of shark attacks and ice cream sales. And if we collect data on how many shark attacks there are every month and how many ice creams we sell every month, let's say it's a beach in Australia, we'll find these two variables are very correlated. And traditional machine learning, what I've called here correlation-based machine learning, will find this association and build a model to predict these two things from each other. So are ice cream sales driven by shark attacks, or are shark attacks driven by ice cream sales? Of course, neither. That's not really true. And we want a model that should dig deeper. We want our models to allow us to ask why and to really understand what's driving each other. Maybe shark attacks are something to do with wind. Maybe when the wind is blowing one direction, the sharks get pushed inland, or wind is blowing the other direction, the sharks get pushed further out to sea. So wind direction should be a factor in there. Maybe ice cream sales have a factor on competing products. So depending on the sales of frozen yogurt versus ice cream, if frozen yogurt's going up, ice cream might be going down. So there's complementary and replacement. And what about sunlight or temperature or season? So obviously sunlight and temperature and season are playing a part in how many ice cream sales there are and how many shark attacks there are, because people go to the beach in the summer and people buy ice creams in the summer. So let me introduce a concept, the concept of a confounder. And now something that drives both shark attacks and ice cream is a confounder. It's causing shark attacks, it's causing ice cream. Sunlight in this case, or season or temperature, is a confounder. And a large part of causal AI, not the only part, but a large part, involves identifying and distinguishing confounders from true causal drivers. So we don't have a situation here where ice cream causes shark or shark attacks cause ice cream. We have a situation where sunlight or season causes both of them. Let me introduce another concept called Simpson's paradox to illustrate why relying on just correlations is dangerous and can lead to incorrect conclusions and incorrect decisions, which is bad if the thing we're trying to predict is the return or the risk of an asset. But before going to asset management, let me start with a simple example, another simple example. And this is about cholesterol and exercise, or how to make people healthy. And say we're interested in collecting lots of data from lots of people, how much of a certain type of exercise they do, how much cholesterol they have. And we see here that based on our population of thousands of people, those that do more exercise have higher cholesterol. So if we were a health authority, we might predict or recommend or make the decision that in order to reduce cholesterol, we should stop people doing exercise. Now, obviously, that flies in the face and contradicts of what we really want to say. So what's going on here? Well, what's going on here is that age plays a role. The age of people plays a role. The younger people in our study have less cholesterol and did less of this type of exercise. The older people in our study have more cholesterol and also do more exercise. So if we control for age, and when I say control for age, I mean putting them into buckets. I mean plotting each group of age individually, we see that the opposite relationship is true. There's a negative relationship between cholesterol and exercise. Age in this case is the confounder. Age has been affecting both the amount of exercise and the cholesterol. But if we didn't know about that, if we didn't know about age, if we weren't aware of the age confounder, we'd make the wrong decision, we'd come to the wrong conclusion, and we'd start proposing less exercise to control cholesterol. So causal AI allows us to do a number of very desirable things. And this is the preview of what's coming up. We can build more explainable models because we can literally see them as a picture. We can build more stable, more robust, more reliable models that don't get hung up on confounders or confused by spurious correlations. And how do we do this? Well, we use data in a smarter way. Quite simply, the mathematics has changed since I was in school in the last 20 years. We can combine them with human knowledge. So we can combine data and human knowledge much more efficiently than we could in the past. And as an aside, this also helps bridge the communication gap between quants and more discretionary managers. So what are the benefits of doing this, and why is everyone so excited, like now, for asset managers? Well, for a machine learning model to accurately model a system, there has to be a pattern in that system. And then that pattern has to be discovered. But if we discover a pattern where none really existed, that's overfitting. And that's a problem because it's not really generalizable. So we really want to discover only the true causal drivers of a system, not just the overfitted correlated drivers. Machine learning works by fitting to the past or by fitting to our training data. And that's essentially curve fitting. And that's okay if the system changes only slowly and the future is just like the past. And in that case, traditional correlation-based machine learning is a really good solution. However, if the system changes more than slowly, and if the future is not like the past, then we do need better models that are more dynamic and understand cause and effect. And then in terms of explainability, traditional correlation-based machine learning, those that were the best at fitting models, i.e. deep learning neural networks, traditionally were also the worst when it comes to explaining themselves. So historically, there was this trade-off between explainability and accuracy. And that's not the case now with causal AI because we can get both. That last point is illustrated by this chart here, which is we could either have a simple model that was highly explainable or a complex model that was perceived to be more accurate but less explainable. And there was this belief that there was this trade-off. We've now moved past that. Causal AI can provide both. So with that, let me move on to a little segue on model risk. But let me just see if I can check the chat at this point. If any questions are in the chat, if there's any clarifications needed, please do type them in the chat. And I will welcome to everyone from where you are. Frankfurt, Netherlands, Japan. Oh, Japan. Utrecht, Scotland. Very good. Type them in the chat if there's any questions and we will address them. But let's talk about model risk. So a little bit of humor, the first fundamental mistake of active management is not having a model in the first place. The second fundamental mistake of active management is believing the model fanatically and not being aware the model might be wrong. Why is that a problem? Well, that's a problem because all models are wrong. As our friend George Box once said, all models are wrong, some are useful. There's a concept called model risk, and model risk can help us understand how wrong a model might be. There's lots of different types a model can be wrong. There's lots of ways of explaining it. I think about it in these ways. I think about process risk, parameter risk, and model specification risk. The process risk is that the world is not the model. The world has randomness to it. The model doesn't. So there's sort of the uncertainty that comes from the process itself. That's process risk. Parameter risk is once we've calibrated a model, the parameters are not known with certainty in the future. They're estimated from training data. If we don't have correct parameters, that's parameter risk. But the most insidious one of all is this one here, the misspecification risk. This means that the equation that we've written down or the structure we have of an equation is just an assumption, and we might have the wrong one. Now, the key point for causality and correlation and so on is that choosing features with association and relying on correlation to do our variable selection or our calibration of the final model, that's basically misspecification risk, or that's my assertion, that we're setting ourselves up and we're making an assumption that we can use association from our training data to create a good model. And that in itself can be a problem, especially in a time varying type environment. So what are the problems then that we're going to describe? Well, the first one, I'm not telling anyone anything they don't already know. Correlation is not causation. We've been telling this to people for the last 50 years. We've been stamping it on students' foreheads. But we've assumed there's not much better we can do. We've sort of made the statement and then moved on. Well, now I think we can do better. The second problem we have is linear modeling. Obviously, the world is not linear. Sometimes linear approaches are the best approximation, but they may not be the most accurate approximation. So we can do better there as well. And finally, as we know, the world is time varying. The world is not a stationary system. There's a concept called concept drift, and I'll say a few words about that. So these are the three problems that causal AI can overcome. I'll describe the problems first, explain what they are, and then we'll move into sort of what is causal AI and how it works. So correlation is not causation. True statement. But that's the problem, because sometimes it is. Sometimes the true causal factors are correlated drivers, and sometimes it's not. The challenge is distinguishing the two. So this little cartoon on the left-hand side, the seagull sitting on the fence. The seagull didn't cause the fence to break, but some computer vision application would recognize a broken fence, would recognize a seagull, and would struggle to understand that one did not cause the other. So in pictures, what does this mean? Well, imagine a large set of correlated drivers. There's a large set of things that are correlated with what we're trying to model. A large set of things that are associated historically with what we're trying to model. However, only some of them are the true causal drivers. Only some of them, a smaller amount. In addition, there might be other causal drivers that we don't know about in our model that were not correlated. And so that's what causaLens' mission is, which is to differentiate between the causal and the correlated, i.e. number 2, and then add on the additional causal drivers, which is number 3. So that's pictorially what we're doing and what is causal AI. But the obvious question that I hope some of you are asking is, how can something be correlated but not causal? What's the difference? So here's a very visual explanation, I hope, of that, which is if we're trying to model Y is an asset, Y is a sector, Y is an asset class, Y is something we're trying to explain, and we're trying to model it using X. X and Y can be correlated for lots of reasons. And correlation can't distinguish between these 5 different examples here. In the first example, X really does cause Y. In the first example, we're okay building a model of Y on X because they're correlated with each other. In the second example, the opposite is true. Y causes X. There's no point building a model on Y if it's the cause of X, because it's the wrong way around. But they still look correlated. In the third example, we've got a system where there's a third variable, that's the confounder, that's causing both X and Y. So X does not cause Y, Y does not cause X. They both appear to happen at the same time, plus noise. So we really want to build models on C for both of them. So in this case, sunlight is the C, and the X and the Y are the ice cream and sharks. Or C is the age, and X is cholesterol, and Y is exercise. So we don't want to build a model of X on Y in this case. In the fourth example, because we've only got limited data, there is a chance that we find a relationship that doesn't exist. We find an association that isn't really there. We only detect it because of the limited data. That's spurious correlation. And the final one is there's a third variable called a mediator, that X causes M, M causes Y. Now we could build a model of Y on X, but X to M has noise, M to Y has noise. So if we're building our model of Y on X, there's 2 sources of noise. We can build a much better model if we just build a model of Y on M directly. We've eliminated one of the sources of noise. So we can build a better model. So the first problem then is that correlation is not causation. The second problem is that we live in a nonlinear world. correlation is a linear measure. I'm sure some of you have seen this in the past. It's a video of a data set that's moving, but that's statistically stable. The means, the averages, the standard deviations, and the correlations between the variables are all the same to 2 decimal places because these are linear measures. So the first 2 issues we have with correlation are that it's not causation and it only captures linear relationships. And that's part of the problem that we want to get over. We want to try to capture non-linear relationships as well. The third one I want to talk about is the idea of a time-varying nature. I'm going to move through this quite quickly, but the idea is that there's something called concept drift. Concept drift is the idea that the world changes. If we build a model on the past, the future world will be different. And the statistical properties of the target we're trying to model change over time. Now, they can change over time for lots of different ways. Assume we've got 2 states of the world, where state 1 is the state we understand, and state 2 is the state that we don't yet model correctly. We can move between those 2 states in lots of different ways. But the fact is we can move between those 2 states of the world. And in the real world, obviously, lots of things are happening at the same time. So the world is changing over time. So we've now got a third problem, which is correlation and causation are different. Correlation captures linear relationships, and the world is changing over time. So those are 3 of the challenges for traditional correlation-based ML. What I want to do now is talk about the solution to causal AI, which is why we're here. So what is a causal graph? And there's 2 elements to this, the causal graph and then what we call a structural causal model. But I'll pause, I'll check the chat at this point. Question, maybe you can reference some interesting research causal AI papers from Michel. Thank you very much. Yeah, absolutely. At the end, I'll show you the academic papers and references and so on. That's a good one. Any more questions, please do type them in the chat. So there's 2 elements to a causal graph, a causal model. The graph itself, which is the picture, and then the equations, which is the structural causal model. So let's talk about those 2. So what is a causal graph? Well, a causal graph is just taking the little elements I showed a moment ago and putting them together on a massive scale, like on the right-hand side here. So here we've got the things causing each other or not causing each other. The only one I haven't shown so far was this one here in the bottom right. This is where we've got 2 parents causing 1 child. So there's 2 things that are driving 1 output. This is called a collider in the literature, and this is the only one that I haven't shown so far. But we can put together these different, very simple relationships in a combinatorial framework and then build up these much more complicated charts. This chart, for example, was how different assets in the S&P 500 relate to each other. So what is a causal graph? Well, at its simplest, a causal graph is a way to visualize equations or mathematical models. And these nodes are our inputs and our outputs. So assume Y is the output, the thing we're trying to predict. All the nodes are potential inputs, or as the statisticians used to call them, the independent and dependent variables, or simply the left-hand side and the right-hand side of the equation. Y is the Y equals X1, X2, X3, X4. The edges between them all are directed, and that means they point from one variable to another. One variable is causing another, or the Y is listening to X4 and listening to X3. In this particular one, Y only depends on X3 and X4 directly. So Y is a function of X3 and X4, but note X3 itself is a function of X1, X2, and X5. So what that means is that even though X5 doesn't cause Y, we would expect to see a negative correlation between these 2, because there's a positive correlation between these 2 and negative correlation between these 2. So we'd see a correlation between these 2, but there's no causal direct relationship between X5 and Y. So we call this a directed acyclic graph. It's directed, there's arrows in it. It's acyclic, which means the edges don't go back on themselves. There's no sort of self-referential there. It's very visual, it's very intuitive, and it creates a language to see causal relationships. But it doesn't end there, because we now need to talk about structural causal models. So let's look at this a bit more formally. Say we have three variables, X, Y, and Z. And X is a driver of Y, Y is a driver of Z. And in addition, there are other things that cause X, UX. There are other things that cause Y, UY. And there are other things that cause Z, UZ. Let's call sort of these UX, UY, and UZ, they're things outside the model. They're endogenous to our model. Sorry, they're exogenous to our model. UX, UY, and UZ are exogenous to our model, and they're independent of each other. There's nothing driving them. We don't know what goes into them. We don't know, but they drive X. So let's group X, Y, and Z. They are our endogenous variables. Let's call them V. Let's call our exogenous variables, let's call them U. And now we've got a set of exogenous, a set of endogenous, and we also have F, our set of functions that relate them all to each other. And this part on the right-hand side is now the structural causal model. It captures the same information, but it also includes details of the functions that quantify the causal drivers. So the causal graph just sort of has direction. It doesn't have the actual functional forms themselves. The structural causal model then has those functional forms. And we can see from this graph that if we know Y, X tells us nothing about Z. So if we're trying to predict Z, we need to know Y and we need to know UZ. If we know Y, we don't need X. So Y is a mediator from X to Z. The key point of this is that the DAGs and the structural causal models together describe the causal relationships. The directed acyclic graph, the DAG, shows us the parent-child relationships between the nodes, and the SCM quantifies the relationships by giving us the functions as well, basically the equations of the edges. So there's two things we need. We need the graph that shows the parent-child relationships, and we also need the equations to define the edges. So how do we do that? Well, there's three main methods. We can do experiments. We can do experiments for each edge, and we can intervene on each node, on each X, and see what happens to Y. Or in the medical literature, a randomized controlled trial. Now, this is not always possible. Basically, in finance and in investing in capital markets, we can't do this. It may be unethical, it may be expensive, and so on. We can't run the economy and then change something and run it again. So we can't do one in the asset management space. But what is very exciting is that the mathematics to do one can be applied to historical data. The calculus that was developed on the first one allows us to do causal discovery on observational data that we see. So even if we can't intervene to change the outcome, we can use the mathematics to perform causal discovery and go beyond the old-fashioned way of statistical associations. So that's causal discovery, and that's the mathematical statistical approach. And the third way to do this is applying domain knowledge, bringing in subject matter expertise, bringing in the discretionary portfolio managers. And this is the bit that is super exciting from an asset management perspective, because this is the piece that gives sort of the historical divide between the quants and the discretionary managers, so the opportunity to come together. And if we do 2 and 3 iteratively, if we do a dialogue between the statistical and then the human, this is what we call human in the loop causal AI. This is where we have a dialogue between the algorithms and the data and the humans in an iterative cycle, so that the machines and the data provide feedback to the humans make decisions that provide feedback to the machines, and the machines then learn the next stage. And this is that kind of iterative cycle that's super exciting. I want to say a quick word about the mathematics. I won't do this justice in the time that we have, but just to sort of illustrate where we're going with this and where this has come from. So the left-hand side of this page is traditional, the right-hand side is more modern. So traditionally, when we assume that correlation is causation and there's nothing we can do, we know X and Y are correlated. We know they've got a joint probability distribution, but we don't know which one causes which. Now, in traditional probability theory, we can factorize this joint probability into either the probability of Y given X times the probability of X, or the probability of X given Y times the probability of Y. And the key point here is that conditioning given something, or the probability of Y given that X has occurred, or the probability of X given that Y has occurred, is saying that we've observed X, what is the probability of Y? That's very different to saying we have done X, we intervened, we made X happen. Now what is the probability of Y? So basically the old language for conditional probabilities didn't allow us to differentiate between seeing something had happened versus making something had happened. And so there's two different situations going on here. Either X might be causing Y, or Y might be causing X, but the language up here doesn't allow us to incorporate that. However, the new language, and this is as a result of Judea Pearl and others, 25, 30 years old now, but only now coming out of academia into industry, was called do calculus. And this differentiates between doing something versus seeing something. So in the old days, we said, what is the probability of Y given we've seen X happening? Now we have, what is the probability of Y given that we have done X, given that we've intervened on X to make it little x? We can observe then what happens when we do that. And if X truly causes Y, then we have the probability of Y given that we've done something to X and little x, that is, and that will have an impact on Y. However, if the opposite is true and the probability of Y and Y is driving X, then if we intervene on X, it'll have no impact on Y because X doesn't cause Y. So if we then test this out and simplify it out, the probability of setting big X to little x given Y and times the probability of Y, if Y is truly causing X, is just the same as the probability of Y in the first place, because changing X won't change Y. So these are two different scenarios. Hopefully you can all see that the real world could operate this way, the real world could operate that way. The old-fashioned way of describing conditional probabilities didn't allow us to capture this directionality, but now we can. I've skipped over that really, really quickly. I've got a bunch of technical notes and intro papers that I can reference at the end to go into more details for that. But what I want to do now is probably jump forward just to summarize where we are, where causal AI is. Then I'll show a few illustrations for asset management and take any questions that there are. So where are we currently? Where's the industry going with this? Well, obviously, causaLens is not the only person doing this. There's a lot of very established companies also playing in this space. The number of papers published has grown exponentially in the last 5 years. This is the number of papers published at NeurIPS, which is the big machine learning AI conference. It's all the more impressive. The data plot here ends 2020. If I plotted 2021, it would be off the charts somewhere up here. And 2022 is obviously coming up soon. Popular themes: causal discovery, causal reinforcement learning, fairness and bias, latent confounders. There's a lot of attention on this right now, typically amongst the experts. You need to be an expert in this to do it. And the causaLens offering allows the non-experts to take advantage of this technology. Some of the papers that we've published recently, and maybe that's a good point to just click to the website. If I show you our website, if you look at our website, under resources, under our causal AI research, there'll be a bunch of freely downloadable papers talking about causality, optimization approach, causal reinforcement learning, how we differ from Bayesian networks. There's an overview of methodologies. There's a lot of open papers that we've contributed to the open source community. So those are our papers and a contribution to this. I'll pause if there are any questions, or I'll dive into the demos. Maybe I'll do the demos quickly, and then I'll leave 15 minutes for questions. So I'll do the demos in 5 minutes to show where this is having an impact for asset management. So there's a number of areas. Here's a few of them. In portfolio construction with causal models, the big thing there is it gives greater explainability to why portfolio construction is doing what it's doing. And we're also seeing higher risk-adjusted returns. But the main focus was on the sort of explainability. For human-guided research is when we're combining these new algorithms for causal discovery, but making it easier for the humans to interact with the mathematical models. We can now literally see models. So this helps some of the historical communication challenges between the quants who live on one side of the shop and perhaps discretionary managers on the other. For orthogonal feature discovery, we can search for new and different and uncorrelated and additive features to improve existing models. We can quickly evaluate new data sets to only onboard truly useful or truly causal features. And there's other areas too in the investment process where if we think about what we've done previously through the lens of correlation, we might be looking at too many or false positives. So for performance attribution, the question is really not when did we make money, but why did we make money? For risk management and sensitivity analysis and scenario analysis, it's about not just replaying history, but by using inputs that are plausible so we can understand the scenarios that are being generated and so on. So let's look at some of these in detail. So in terms of portfolio construction, the two well-known approaches that most people start from are either Markowitz mean variance or hierarchical risk parity. Now, Markowitz mean variance obviously uses a covariance as a risk model, and what's behind a covariance matrix? Well, there's a correlation matrix hiding behind the covariance matrix. And hierarchical risk parity, that also uses correlation to cluster similar assets together as the distance measure. So we build them up from the pairwise correlations. So both of those are depending on a correlation matrix. And we've just spent some time discussing why we want to use not correlated and not correlation, but rather the smaller set of true causal drivers than the larger set of correlated causal factors. If we're using correlation, there's a risk of overfitting to our training data. And the other thing is that correlation is symmetrical. If A is correlated with B, B is correlated with A. And the relationship between the assets we have may not be symmetrical like that. That's a huge topic that I can certainly go into in more detail, but I'll quickly sort of move to the other examples and show a few demos as well. So this one here actually is a screenshot. And what I'm doing is I'm uploading some asset level risk factors to a universe and then using hierarchical clustering to look at them. And then here we have the risk hierarchy according to a certain causal risk model. It's called graphical lasso, and which discovers causal relationships after the spurious correlations get taken out. So in this particular case, this particular asset is related most directly to these 6 assets, and we can highlight each one and sort of look around. And the ones that don't seem to be connected to anything are basically the ones that are purely idiosyncratic based on this risk model. Now that gets very exciting sometimes when we're dealing with managers of managers or multiple strategy risk models, because people are looking for uncorrelated things. The next one is about looking for risk factors themselves. So I'm uploading portfolio returns and I'm uploading portfolio risk factors. And then this gives us a very simple, small chart. I'll just pause there. Oh, missed it. Which is of the 8 factors that I'm going to be looking at. You know what? I'll skip forward to that one. Until now, the graphs we looked at were just sort of simple 2 layers, one layer of parents, one layer of children. I'll now show a few multi-layer ones. This particular one is around human-guided research, and it allows, this is how the humans actually interact. So the humans, the domain experts, can inject their knowledge on what should the parents be. Should they be positive relationships or negative relationships? Then the machine goes away and sort of fills in the gaps and iterates through and presents some information back to the human to inject some more knowledge. And this allows the quants and the non-quants to collaborate very efficiently. So here we're resolving some edges. The language resolving edges basically means specifying the edges the machine in itself can't classify as positive or negative with any great certainty. So it asks the human, do you think this is positive? Do you think this is negative? So as I mentioned, this helps the interaction. It very quickly speeds up a research and innovation process. I'll say a quick word about causal risk assessment. So this is a very exciting use case that can be applied to any model that might be a traditional model. So we can either use causal AI to create the model, or we can use causal AI to assess the model. So we can take a typical model and we can ask questions like, what are the causal drivers of this model? Are there any spurious correlations in there? Under what circumstances will the models fail? How can the errors of the model be explained, and so on and so on. So that's causal risk assessment. This is very interesting to a lot of the banks these days when it comes to model validation. Speaking of the banks, obviously a lot of banks in Europe, the US and the UK and everywhere are performing stress tests for regulatory reasons. So we've done work for banks in terms of how to help them with their regulatory stress testing. I'm mentioning this to asset managers because when it comes to portfolio stress testing, it's exactly the same. We can build a causal graph based on our macro factors. We can create different scenarios. In this case, it is the regulatory ones. And then we can see what the outcome is likely to be with certain probabilities and uncertainties. The last one I'm going to mention briefly is causal boosting. Causal boosting is when we take a light gradient boosting machine and we enhance a model by saying, taking the residuals and taking the residual part of an existing model and trying to explain the residual. So this has been of interest to some of our clients where they've got models. They don't want to share with us the model, but they're happy to share the residual of the model. So we never see the model. We don't know what assets they're trying to create, but all they do is give us the residuals, the bit they can't explain. And then using different data sets and causal discovery, we try and explain the residuals. If we can explain the residuals, then obviously there's some orthogonal features that we found, and they can make a better model that way. And that gives complete security of IP of the model to the client. So maybe I'll wrap up and then open to questions. So to wrap all this together, to make decisions, we need to consider different scenarios and answer what-if questions and have better models that can anticipate the future. Conventional correlation-based machine learning learns from the past and is confused by spurious correlations, hidden confounders, and so on. We really want to know why happens because X happened. But unfortunately, traditional correlation ML gives us why happened when X happened. And those are two different things. We want ex-ante explainable models in order to trust them. A lot of the explainable AI literature these days is about building models ex post. So a model of a model. What we really want is ex-ante explainable models that are inherently explainable. And for causal AI, we build DAGs and FCMs. Big picture, causality is a necessary condition for general AI and the ability of machines to reason. It's going to be a big thing in the next 5, 10, 15 years. But long before that, it is certainly helping with several challenges in the asset management industry today. So things like portfolio construction, human-guided research, evaluating alternative data sets, performance attribution, and so on. Maybe I'll pause there for any questions. If anyone has any questions, please do unmute yourselves and ask them either on camera or in the chat.
Hi Ben, this is PJ. I was wondering how the level of computing compares in your causal inference versus the standard methods that you showed in your examples. For example, in the portfolio construction, if you compare this hierarchical risk clustering versus your techniques, does it take much more time? Or
the computational side.
Yeah, the computational side.
Computational complexity.
Yeah.
Absolutely. So one of the features of this approach is it's very computationally expensive. So behind a lot of the techniques is sort of a combinatorial approach, which brute force is heavy. So the part of the skill and part of the experience that we have is in the heuristics to know how to treat the search space intelligently. So yes, the answer is yes, it's very computationally expensive, but we're now at the stage where, depending on the problem and depending on certain heuristics, there are shortcuts through that search space.
Okay, and the level of the degree of complexity, I mean, how does it compare to the standard techniques?
In terms of raw compute time?
Yeah, more computing time. Is it what's the magnitude?
It depends. It's not. I mean, I wish there was a quick answer to that, and I could say 5 times or 10 times. Yeah, I wish I could give you a number. There's lots of different techniques. So there's no. It's not like there's one single causal AI technique. There's multiple different approaches depending on the problem set. So for cross-sectional data, for time series data, for slowly moving data, for fast-moving data, for et cetera, et cetera, et cetera. One of the things that we've spent a lot of time and a lot of effort on is sort of the meta heuristics that know which algorithm to use depending on the problem to be solved, and how to simplify the search space to look for the most likely candidates. If you want more, I can follow up if you have specific, if you say something along the lines of, my portfolio is X assets, I want to use this many features, this many factors, and so on. I can give you some examples and follow up after this, but it's a fairly broad, open-ended question.
Okay, but would you, if you would take a toy example, for example, here, could you do that on? Could I do this on my standard PC, or should I immediately go to I don't know, a GPU farm?
Got it.
Yeah.
If you were talking to causaLens, and if we were using our software, you could do it in like a matter of seconds or minutes.
Okay.
It's point and click. So if you're looking at sort of 100 assets, 50 assets, 100 assets, it's point and click. If we're doing sort of heavy, deep research, it's sort of batch jobs to be scheduled overnight. But the offering that causaLens has, we basically build decision apps that might be based on portfolio construction or human-guided research or performance attribution. We build sort of standalone apps that are web hosted, that are point and click. So you'll do it, you'll bounce around, and you'll see the results like in seconds.
Okay, thanks.
I see a couple of questions that I'll read out. So from Alexander, thank you, Alexander. You mentioned causal reinforcement learning. Does it mean that normal reinforcement learning is correlation-based only? If yes, could you try to explain why, and what is a good paper to understand the difference? What I'm going to do to make things easy, I will simply paste in the paper on causal reinforcement learning in the chat. That might be the easiest way to do it. There's a recommendation. So Alex, there's a paper on causal reinforcement learning. Essentially, the answer is yes, which is traditional reinforcement learning looks for associations. If we use the causal approach, it's looking for the true causal drivers. Next question from Marco. Thank you, Marco. How do you deal with latent variables? Often we're given a certain set of variables, but it's quite possible there are some other variables not in the data set that could have causal relevance on the variables of interest. How do you find those? Okay, great question, brilliant question. So to give you an example of a latent variable, maybe value is a latent variable. Maybe our equity factors are a latent variable, value, growth, momentum, low vol, and so on. All we can really see are the observable metrics. So for value, it might be price to book or PE or book to value or so on. So we've got various metrics that we think drive our latent variable, that we think drive our returns. And the way we do that, different algorithms have different assumptions behind them. Some of the causal algorithms have an assumption of causal sufficiency. The definition of causal sufficiency is that we know everything we need to know. So some make that assumption, but not all. So there are certain algorithms that can relax the causal sufficiency assumption. So the quick answer is, how do you deal with latent variables? It depends on the algorithm chosen. Maybe I can follow up with you with a more specific example on equity factor models, where we've got a worked example where we talk about those latent, the typical factors become latent variables, and then the data becomes the real data we can see. So Marco, if you want to reach out to me, I'll follow up with you on that. From Nick, I have 2 questions. You once mentioned concept drift, and I was wondering whether causaLens can handle paradigm drift or shift. For example, like how paradigm in physics changed from Newton to Einstein, Einstein to quantum. I believe that paradigm in social sciences, in social scenarios, shifts more commonly. So let me address that one first. So concept drift in finance. Finance versus physics. I think there's two, maybe I'll say something philosophically first, and then I'll address the question. So I think there's 2 schools of thought when it comes to modeling in finance. On the one side, that there's a school of thought that says, if only we had a better model. There's a factor out there we don't know, or if only we had more frequent data, or if only we had this data set we don't have. There's one model that's the holy grail that we'll get eventually. That's one philosophical starting point. There's the other approach, which is, you'll never have the right model. The best you can do is have model monitoring to tell you when your model's not working. Now, I'm very much in this camp. I don't subscribe to the camp that there is a system behind finance that if we collected enough data, we would have the answer to everything. So what my response is, if we have decent model monitoring, and what do I mean by model monitoring? Model monitoring is designed to detect when the model is not performing as intended. If something changes, red lights start flashing. It's not about, when you start losing money, because if your model is not performing as intended, you want to know that before you started losing money, obviously. So what are the other attributes of your model? How many positions do you expect? What's the holding period? What's the slippage you're incurring? How many fills are you getting, and so on. So there's certain attributes you have around your model that will sort of start to change probably before the model deteriorates too badly. And so with decent model monitoring, you'll then know when the things have started to go wrong. How we build that into the model is we can build the model monitoring into the model itself, which is the feedback loop, which is, there's 2 states of the world. I sort of skipped over this very, very quickly. If we assume one state of the world, we have a good model, the other state of the world, we have a bad model, then all we're doing is monitoring when the model is behaving as intended and when the model is becoming self-aware enough to sort of turn itself off. That was a very quick question. I think we're coming to time. So I'll pause at this point. I'm more than happy to send a follow-up list of recommended reading. I prepared a list of our technical briefing papers for one of our clients in terms of what order they should read things in to sort of, start with the basic stuff and get more complicated. If that's of interest, please reach out to me and I'm happy to share that. But maybe I'll stop at that point.
Okay, thank you, Ben. Yeah, that was very good. I think a lot of food for thought. And I think you are on LinkedIn and people can reach out to you directly if they have any further questions. So thanks again.